Hi everyone, hope you're doing well. Today I'm going to be doing a lesson for you guys over activity 9D. So 9D is actually more of a conceptual lesson this time. There's not going to be as many computations, so I hope that you're able to follow along with this video and really engage with some of the thinking about the concepts that we're talking about here. So today's lesson is going to be over something that you may have heard before, which is this idea of correlation versus causation, or you may have heard correlation does not imply causation. And this is actually a really, really, really important idea, but I think phrasing it like that, correlation does not imply causation, makes it sound much more confusing than it is. So we're going to unpack this idea today. And actually, the lesson starts us off with a pretty serious and pretty sad example of this, but it's a real example, and it shows the true danger of assuming we have causation when in reality we have correlation. And we're going to talk about what those mean today. So, um, some of you may have heard of something called SIDS, or sudden infant death syndrome. So this is something that is very unfortunate, and it basically is a cause of death for a lot of infants where they die, but doctors aren't exactly sure what's happening. So one thing that they realized is that they noticed that a lot of babies that were dying from SIDS have enlarged thymus glands. And so, by noticing that, we would call that a correlation. So, what they assumed was that there was a cause and effect relationship there. They assumed that the large thymus must have been what caused them to die. And so, in order to try to treat that, they began to shrink the thymus of some babies using radiation to try to fix the problem. But this ended up not working and actually causing a high mortality rate and leading to more deaths or complications for the children once they reached adulthood. So it turns out the thymus actually was not causing SIDS. Something else was causing both of the things to happen. And by assuming that the thymus was the cause and by targeting the thymus, it actually had very unfortunate side effects. And so this is just an example of why we need to be really careful before we assume that one thing is causing another thing just because there seems to be a connection or a relationship between them. So this example was really serious, but we're going to now jump into some less serious examples to try to get the same idea. Just to kind of redefine these words, scientists noticed a correlation between the size of the thymus and occurrence of SIDS. What they noticed was that babies that had SIDS more often also had enlarged thymus glands. That correlation is a relationship between them, but it does not mean that they are causing each other, that one is causing the other. So just try to think of anything that you've observed in your life that these things seem like they might be related, but one does not actually cause the other one. So you can think about that, and I challenge you actually to try and think of some of these because they actually come up a lot more, and they're more common than we realize. But it can also be kind of hard to think of one on the spot. So see if you can think of any examples. But we're also going to move on and look at a lot of them during this activity. So that's what we're going to do right now. So we're going to look at a few statements, and we're going to decide whether we think that there's actually a cause and effect relationship happening, or maybe there's just a third thing that's causing the two to occur, a third unrelated factor. Okay? So for each of these, I actually want you to pause the video and just look at each of these and see what you think. See if there's a cause and effect relationship going on here or not. And actually, for some of these, for at least one of these, it's actually not entirely cut and dry. It's not entirely clear what the answer is. Okay? So pause the video for a second and try to guess on your own. But now I'm going to go over them just so that we can start to see how this can be a little bit confusing or tricky to figure out in the real world. So for part A, someone notices every time I eat chocolate, it makes my face break out. So this one I like because it actually might seem like these aren't related at all. That eating chocolate wouldn't cause your face to break out, but actually I know that chocolate has oil in it, and anytime you eat something oily like pizza or chocolate or anything, for certain people that can make them break out that oil. So this is an example of where you might not have known that fact, but over time you notice, hey, every time I eat these foods, my face breaks out. And so you found this sort of relationship, and it turns out that one actually is most likely a cause and effect relationship. Now, does this prove a cause and effect relationship? No. It takes scientists looking into this and seeing what causes breakouts to determine that eating oily foods can cause breakouts. But this is a correlation that we can observe that actually does align with a causation. Now, this one, for part B, honestly, I'm going to leave it open as an opinion. Now, I'm going to share my thoughts on it, but truly, I think this is one that you can. This talks about psychology, and so anytime you talk about psychology, we really don't have a lot of definitive cause and effect proof evidence in these situations. So a lot of it is looking at correlations and deciding whether they're causation. So there have been studies that could show that watching violence on TV leads people to be violent in real life. Now, already the newspaper has done something irresponsible. What they should have said is that studies have shown that people who watch violence on TV also tend to be more violent in real life. Because that is what the study had the ability to show. This word leads is the problem. Because there may be a correlation between watching violence on TV and being violent in real life. But does watching the violent TV cause you to be violent in real life? Now, I think some people still believe that this is a cause and they would try to argue it. But I just want to put out there that I'm an example of somebody who, I don't watch a lot of violent TV, but I play video games a lot. And there's violence in video games. But I am not very violent at all in real life. And so when I see part B, I say, well, yes, maybe people who watch a lot of violent TV can be more violent in real life. But would it not also make sense that the people who happen to be violent in real life would also enjoy watching violent TV? So couldn't this go the other way around? Maybe the people who are violent in real life, that causes them to watch violent TV. So just by looking at this correlation alone, we don't have a proof statement. And this is not enough to justify that watching violence on TV makes people violent. And I know enough people that watch violent TV that aren't violent at all in real life. And so for me, I say there's not a causation here in that this newspaper did a bad job. But you're free to agree with this if you want. There's not enough data, I think, to say one way or the other. Now for part C, this one I like as well, and this is the title of the lesson. Why are you wearing the same socks? So a baseball player tells his friend that he did not change socks for 3 games, and the team won all 3 games. The player concluded that wearing these socks caused the wins and decided not to wear a clean pair of socks for the next game. Now, obviously, we can think about this logically, and we know that, well, here's the thing. We don't know for sure, but with almost certainty, we are almost sure that wearing the same socks that are dirty does not cause you to do better at baseball and does not cause you to win. There's just too many other factors involved in the game to lead to that. And also, winning one game can make you more likely to win the next game if you start building a streak and build confidence. So even that could be more of a cause than the socks. So I would say not a causation here, as I think most people would. But what I love about this lesson and the idea is that really, really, there could be some really weird connection between the player and his socks. Maybe the way those socks feel are more comfortable for him, and so they play better. Or maybe there's also something called the placebo effect, right? So maybe just because this player is wearing these socks and believes that they're lucky, that could actually make them more confident and change the way that they play the game. So even as silly as this seems, and it's most likely not a causation, the idea is that these correlations don't tell us any information about whether there's a causation or not. Just like we can't say that for sure that there is a causation, we also can't really say for sure that there's not. We can just be critical and use our judgment. And that's why it's so important, this lesson, that you're able to make these judgments. So that if you ever see an article like this that is claiming that one thing causes something else, you can be a little more critical and say, is it really a cause, or do they both just happen to be related somehow? Okay? So, we're going to talk about something called the correlation coefficient. So if you remember in lesson 8, I believe it was lesson 8D, we looked at some relationships and trend lines, and we looked at something called an R-squared value. R-squared was the square of the correlation coefficient, okay? So R-squared told us how strong a relationship was between two variables. A 0 meant there was no connection, and a 1 meant there was a very strong connection. The correlation coefficient is going to be exactly the same, except now we can go from negative all the way to positive. Whereas the R-squared, the coefficient of determination, was only positive. So what this means is that we have all the way from a 1, which is a very strong positive correlation. What that means is when one thing goes up, the other thing goes up. So they increase together. Then on the way, they can go down to 0, which will indicate that there's no connection at all, or no relationship at all. Going further, we can go down to -1. -1 would be a very strong correlation, just as strong as the positive one, only this time it's a negative relationship. And we're going to look at what that means a little bit more. So a negative relationship means when one thing goes up, the other thing goes down. So they kind of work against each other. So let's look into this. So these scatter graphs you might recognize kind of from the activity we did in lesson 8. So here they're kind of scattered everywhere. There's no correlation. Here they call this a very weak correlation. Why do they say that? Well, if you look, it looks almost as scattered as this one, but you have these sort of almost, let me draw this in here. You have these almost tiny little triangular regions that you can imagine here, right? So they're saying almost you could imagine that this has some sort of negative correlation. But really, they say very weak, and they mean very weak. It's almost indistinguishable from this one. And so I actually don't know that I would call this a weak correlation. But here, going to just regular weak, you can actually see now, even though this is very scattered, it does totally make sense to call this slightly positive because it trends just a little bit upward. And as you can see, this is what a stronger positive relationship would look like. So do you see as we get stronger and stronger, the points get closer and closer together, like they start forming a line. Here is a weak negative correlation. So you can see it's just like the weak positive correlation, but now it's heading downwards. And this strong negative correlation, again, it's going downwards over time, but more tightly packed in. So this would have a correlation coefficient closer to, say, -1. Not exactly -1 because these aren't a perfect line, but maybe like -0.9. And maybe this would be something like +0.8 or something like that. I'm just making these up. But maybe this one would be something like +0.3, a little bit closer to 0. So again, you're not really having to calculate these. These would be given to you, but it's important to understand what they mean. This is very close to -1 because this is a very strong negative correlation. And this is closer to 1 because this is strong positive. So with these pictures in mind, let's look at some of the relationships here and try to tell if there is a positive, negative, or 0 correlation. Now, again, I want you to pause the video and try to think of these on your own, but I am actually going to talk through them afterwards because these can be really tricky. Again, going back to the idea of causation versus correlation, don't be thinking that these have to cause each other in order to be correlated. So this is a great example. One variable is the carbon dioxide levels in the atmosphere since the 50s. The other variable is the obesity levels in the US since the 50s. Now, right off the bat, you may have been tempted, if you pause the video and tried this on your own, to say 0 correlation because you thought, what the heck does carbon dioxide have to do with obesity? And you're right, there's not really a cause and effect relationship here. One of these things isn't causing the other. But what are both of these things doing over time since the 50s? Let's think of it. What has happened to the carbon dioxide rates over time since the 50s? Well, they've increased, right? They've gone up. Global warming, climate change, the carbon dioxide levels have definitely increased. How about obesity levels in the US since the 50s? This is another thing that has undeniably increased. We know that obesity has gone up in the US since the 50s and become a big problem in the US. So these are two variables that both increased. And so actually, if you graphed over time the obesity levels and the CO2 levels and compared them in a scatter plot, you might see something. It wouldn't be a straight line, but it might be sort of a cluster like before, going up like this, maybe something that looked like one of these. Why is that? It's purely just coincidence that they both have been going up over time. CO2 levels have been going up for one reason, and obesity levels have been going up for another reason. Maybe those reasons have a connection, maybe they don't at all. But as far as the correlation is concerned, these would actually be positively correlated. When one went up, so did the other. They went up together, they increased together. And again, this totally emphasizes the fact that this is not necessarily a cause and effect relationship. So someone could try to make a study where they compare CO2 levels with obesity levels over time, and they say, look, whenever the CO2 levels went up, so did the obesity. They must be causing each other. But that would be pretty silly without any other scientific data to back that up. These just happen to be positively correlated. So let me cross off 0. The answer is positive, because they've both gone up over time together. Now, how about this one? This might be familiar to something I talked about in the last lesson, 8D, last week. So the height in school-age children measured in inches and measured in centimeters. Remember, we talked last time about how inches and centimeters are exactly related to each other. There's a perfect correlation. So this we'd expect to have a perfect correlation of 1. And why positive 1 and not negative 1? Well, this is where you have to think about if it's positive or negative correlation. When your height in inches goes up, what happens to your height in centimeters? It also goes up by the same ratio. So those increase together, so it's a positive correlation. Now let's look at part C. The age of a car and the value of that car. So take a second to think about this one. What happens to the value of your car as your age goes up? Typically, as the age of a car goes up, the value goes down. You lose value on your car over time. So this one, we might expect to see some sort of cluster of points that is trending downward. Again, it might not be an exact straight line. It might rather be like points scattered around, like something like this or something like this. But the idea is that they're going to be negatively correlated this time, because when your age goes up, the value of the car goes down. They're related to each other, and in fact, this one is a cause and effect. The age is what's causing the value to go down, but it's a negative relationship. So this would have a negative number as the correlation coefficient. So here's just one last example that I actually think is a really fun example to think about and revisit that idea of causation versus correlation. So basically, this student tells a teacher, you better be careful. There's a high correlation between eating ice cream and drowning. And the teacher obviously is confused. What are you talking about? How does eating ice cream cause drowning? And this person says, well, don't you know that the highest days with the most ice cream sales are also the days that have the most drownings? So why is that? Why could that be? Does ice cream really make people drown? No. So try to think about it. Pause the video and try to think. It's kind of fun trying to think what the connection is. But I'll go ahead and spoil it. When do people normally eat the most ice cream? In the summer or when the weather's hot. Also, when do people swim the most? Also in the summer or when the weather's hot. So because ice cream and swimming are activities that are both summer activities, they're going to correlate with each other. And drowning is related to how many people are swimming. So that is the connection between ice cream and drowning. Again, the ice cream is not causing the drowning. Okay, so I was actually thinking of ending the lesson here because this is really the idea that you need to get out of the lesson. But just conceptually, these last few things that they ask you to do, um, well, I think they might be a little bit confusing if you do it on your own. They really hit home a lot of the stuff we've been talking about. So really quickly, what I just want to do is walk you guys through the last question here and just show you what they're talking about, so you can think conceptually about all these things that we've been having you compute and what it means. Okay. So we collected data on the weight of cars and their miles per gallon on the highway. So we can create a scatter plot of the data, and I went ahead and did that for you guys in Excel. So just a reminder of how you can do that. I've got the weights here and the miles here, and when I select all of this and create a scatter plot, this is what I get. So as you can see, I've already got this line in here, a little bit of a spoiler. But the data seems to be going slightly, ever so slightly, trending downward. But if we think about it, that should make sense to us, that there could be a negative correlation. Why is that? Because, well, actually, I don't know a lot about cars and how they work. But I would assume that the heavier something is, the more fuel it's going to take to move it, the more energy it's going to take to move it. And so I'd expect that they would get a little less miles per gallon because something's heavier and so it's harder to move. This is really interesting because I'm a perfect example of someone who's not an expert in this field and I'm just looking at the data. So I may be tempted to say that there's a causation relationship here, but because I'm not an expert, I could be wrong. But this is just based on my intuition. I do think that a heavier car would make sense to have a lower miles per gallon because it's heavier. So there is a negative correlation here that may or may not be incredibly strong, but pretty okay negative. I mean, they're not completely scattered, so it's a pretty decent negative correlation, and that implies that the heavier a car is, the less miles per gallon it gets. That would be a contextual sentence. And I thought maybe this is a cause and effect relationship, but I don't know much about cars. Does anyone else know any other variables, any hidden factors that might cause this relationship? Rather than it being directly caused by the weight, maybe the miles per gallon is related to the car parts that are used or the engine that's used, and maybe different engines that get different miles per gallon weigh different amounts. There could be lots of other things that would affect these two things. Maybe the age of the car as well, and maybe different customization options for the car. So think about all those factors and how maybe this isn't a direct cause and effect relationship between weight and miles per gallon. But how does this tie into what else we've been doing? So what they want you to do is pick two ordered pairs from the table and find a line that passes through them. So let me show you what that looks like. I went ahead and did that. So I set it up here so that basically whatever points I copy over into this column, Excel will create a line going through those points. So I went ahead, let me delete this really quick. This was what the scatter plot looked like before. And so I picked these 2 points and went ahead and created a line through them. But I could have chosen any point. I could have, instead of those 2 points, I could have chosen these 2 points and drawn a line between those. Or I could have chosen these points. So I could choose any 2 points and connect them with a line. And you see those lines sort of match the trend, but in different ways. So I had chosen just these 2 points because to me they looked like they did a good job of going through the rest of the points. But it's completely up to you which points you would pick. But why would I do that? Well, my goal is to use that line to sort of approximate what a car's miles per gallon might be based on just knowing its weight. So I've got the equation of my line here. We see this negative 6.01 times 10 to the negative 3. This is a very tiny number, times x plus 47.5. So here, check this out. If I enter that equation negative 6.01 times 10 to the negative 3 times, now what is our x value? The weight, right? We're plugging in the weight, plus 47.5. If I plug this in and I drag this out, this is giving us what that equation tells us would be the miles per gallon. And we can compare to the actual miles per gallon. So if you notice, on the point that corresponds to 3,489 and 28, this point right here, our line was too low, right? Our line went below this point. And similarly, when I plug in this value, that value that it's giving me is too low. It's lower than 28. So some of these values are low, some of the values are a little too high. These values are almost exact because these are the ones I used to create my line. So this line is sort of a predictor of the miles per gallon, but it's not perfect because this wasn't a perfect linear relationship. But what I can do is I can use this line to make guesses about other values of miles per gallon. So, for example, what about a car that weighs 2,296 pounds? Let's use our formula to figure that out. So if I go ahead and I take this equation and I come over to a blank here and I punch that equation in, but this time for that x value, instead of using a value from my table, I'm going to use the value they gave, which is 2,269. When I plug that number in and hit enter, I get this number, 33. Okay, about 33 miles per gallon. Now let's look. Is this an example of interpolation or extrapolation? So remember, interpolation is when we use a trend line to make a prediction about values that are within values we've already collected data for. And extrapolation is when we're using it on anything that's outside of the range that we've already looked at. So this value, 2,269, it is not really at all within the range of what we looked at. Every number we had in our table was above 3,000. And so we're actually looking at something that's way over here off our chart. So this is going to be extrapolation right now. We're going outside of our data. And of course, there's always a risk there that maybe something's going to change outside of here because we can't see the trend anymore. So that is an extrapolated number, that 33. And in fact, they gave us a website where we could go look at this. And here we see that the actual miles per gallon is 35. So actually, even though we were extrapolating, we didn't do too bad of a job. 35 is pretty close to 33 when you look at, how close our other points are on our trend line. It's not too bad. So even though we were extrapolating to something outside the data, we're able to pretty much predict the miles per gallon of this car just looking at that table. So that's pretty cool. And lastly, just a little bit more practice looking at these slopes and y-intercepts. Look at the slope, this very tiny negative number. This is just a very tiny negative decimal number. But what that number tells us is apparently that's saying that every time you increase the weight of your car by 1 pound, your miles per gallon will decrease by about this number of the slope, okay? That y-intercept, what does that mean? Well, the y-intercept would represent the miles per gallon of a car that weighed 0 pounds. So, is there such a car? Are there any cars that weigh 0 pounds? No. So this is not possible. So this is not actually going to be a meaningful data point for us, this y-intercept. And lastly, comparing your answers to Part B and Part G, what they mean by that is going back to Part B, remember we said there was a negative correlation, and that slope is also negative. And that is the connection they want you to see, is that if we make any sort of trend line, its slope is going to match the correlation. So if there's no correlation, we should get a flat line that has no slope. As that line becomes negative, it starts to suggest that there is a negative correlation. If that line's positive, it suggests a positive correlation. So that's it for the lesson today. I hope I didn't ramble too much and that I did an okay job of getting these ideas to you of correlation versus causation, because I do think that more than something that you need to apply for this class or for an exam, I really think these are concepts that are going to help you make sense of things that you discover in real life. So I hope you guys have a good one. And as always, let me or your instructor know if you have any questions. Thanks.